One of the most elegant demonstrations of adipose tissue's essential role in systemic health is its continuous, dynamic neuroendocrine communication with the brain and other key metabolic organs, a sophisticated feedback system that positions fat not as a passive energy depot, but as an active coordinator of whole-body homeostasis. Through this bidirectional crosstalk, adipocytes sense the body's nutritional status and relay signals that fine-tune both behavior and organ function, ensuring energy intake, expenditure, and nutrient distribution remain balanced across changing conditions. A prime example of this neuroendocrine dialogue is the hormone leptin, secreted almost exclusively by adipocytes in direct proportion to fat mass. Rising leptin levels during times of energy surplus signal the hypothalamus, particularly the arcuate nucleus, to reduce appetite and increase sympathetic nervous system activity, which raises energy expenditure through mechanisms like thermogenesis in brown adipose tissue. Conversely, when fat stores shrink, leptin falls, lifting appetite suppression and reducing energy expenditure, driving the individual to seek food and conserve energy. This elegant feedback loop enables adipose tissue to function as a long-term gauge of energy reserves, aligning feeding behavior and metabolism with current energy stores to maintain stable body weight over time. But the communication does not end with the hypothalamus. Leptin and other adipocyte-derived hormones, such as adiponectin and resistin, modulate the activity of brainstem and cortical circuits that influence reward-driven eating, stress responses, and even mood, highlighting how adipose tissue affects both homeostatic and hedonic drivers of food intake. Beyond central regulation, adipocytes engage in extensive endocrine crosstalk with peripheral organs. For example, leptin and other adipokines influence pancreatic SS cells, modulating insulin secretion in response to nutrient availability. Meanwhile, signals from adipose tissue also affect pancreatic A cells' release of glucagon, further fine-tuning blood glucose levels to match energy demands. Meanwhile, the brain sends signals back to adipose tissue via sympathetic and parasympathetic nerves that innervate fat depots. Sympathetic activation triggers lipolysis through norepinephrine release, promoting the breakdown of triglycerides into free fatty acids that can be used by other tissues for energy. This neural input is essential during fasting, cold exposure, or exercise, when immediate energy mobilization is needed. Conversely, parasympathetic signals may support fat storage during periods of rest and energy surplus. This two-way communication ensures that adipose tissue is not merely responding passively to hormonal cues, but actively shaping systemic energy dynamics. Disruption of this neuroendocrine feedback, such as in leptin resistance associated with obesity, leads to a breakdown of the energy balance system, resulting in unchecked hunger, reduced energy expenditure, and worsening metabolic dysfunction. Conversely, restoring proper leptin signaling, or enhancing the sensitivity of central and peripheral circuits to adipose-derived signals, holds great promise for correcting obesity and metabolic diseases. Altogether, the continuous hormonal and neural dialogue between adipose tissue, the brain, and peripheral organs illustrates that fat is an indispensable neuroendocrine organ, integrating metabolic signals and orchestrating coordinated physiological responses. Far from being a harmful burden, healthy adipose tissue serves as a master communicator that aligns energy intake, storage, and expenditure with the body's needs, playing a central role in sustaining metabolic health and systemic homeostasis.